Okay, guys, I'm going to be out of school again, unfortunately. I'm sorry. And so, what I want to do is I want to walk you through some pretty important and somewhat complex introduction to cases where the block or an object is not sitting on a horizontal surface. So, we're going to put the block on an inclined plane. Now, again, this is a little bit more difficult, but not really. It's a level of complication. It's not a level of difficulty or misunderstanding. if you if you try to just memorize stuff, that can be a little tricky. So I'm going to suggest that what you do is you try to think about the situation. You do have to memorize some equations. I'll show you where they come from, but what you don't want to do is try to memorize all these cases. You want to say, I understand what's happening. I understand what law applies, and this is how I'm going to attack the problem. So I'm going to walk you through inclined plane problems. I will talk about this when I get back. I just want you doing something meaningful while I'm at the doctor's office, so you're not wasting the day, because we do need to plow ahead and get to the holiday break with some content down. So in your notebook, I would clear off a brand new section of your notebook, titled Inclined Planes, and I'm going to walk you through the derivation of the equations you need to do these problems. So first of all, it's like everything else in physics. It's just kind of common sense. So if I look at a person skiing on a green slope, and I look at somebody skiing on a triple black diamond slope, the question is, well, which skier goes faster? And obviously, the person on the steeper hill goes faster. But the question would be why? Why is the steeper hill make you go faster? So we have an inclined plane that has a very small angle. And we have an inclined plane that has a very steep angle. And here are the blocks. Here's a child on the surface, and we're going to draw a free body diagram of the forces. Here's a person on a steeper slope. We'll draw the forces, and I think you'll see why that happens. And again, that's the beauty of physics. Explains that. So one of the things you got to remember, and we didn't do all these examples, but we have to remember that when we have things at angles, we need to break them into x and y components. We need to break them into components that are useful. So when we did a projectile, we said, hey, we shoot the ball at a certain velocity. We need to look at the x component, and we need to look at the y component, and then we can look at how that object behaves in the x and y axes. We didn't do tension problems this year, but if I had a cable holding a couple of cables holding up like some mass on a string, we could look at the tension in the cable at x and y components of those tensions. And if I have a block on an incline and we apply a force at an angle, we could say how much of that force is going in the x and how much is going in the y. So we need to think about components, and usually we use x and y axes because we live in a horizontal and vertical world. We're going to do the exact same thing, but now we're going to be looking at a block on an incline, and we're going to abandon the xy axis and then use the axes defined by the incline. And you'll see what I mean by this. So in your notebook, again, you want to draw this picture relatively large. Don't draw a one line or two line. Take about a third of your paper and draw a block on an incline. We're going to look at the free body diagram of this block placed on this incline. So here's a surface that's inclined to the horizontal, and we're going to look at what's happening in this situation. I'm going to move that head out of the way. Now, when you do this, I'm going to define two new axes. So normally we use the x-axis going horizontal, and we use the y-axis going vertical. But it turns out for these problems, it's much more convenient to use. Let me just get my pens queued up here, right? I'm going to do some fine point. We're going to define new axes. So what we're going to do is we have this surface, and we're going to define an axis. And I would wait to draw this. Wait until I'm done, and then you can draw this in your notes, and you can stop the video and make the nice picture. So I'm going to draw the axis. Rather than using x and y, like we normally do, or x and y axis, I'm going to make an axis here that is going parallel to the incline. And I need a name for this axis. Normally I'd call it x or y, because x and y are horizontal and vertical, and this is inclined. I'm going to call this the p-axis. P stands for parallel. So that's the parallel axis. I'm going to call it P. I'm going to call it P from now on. Then I want to pick another axis that is at 90 degrees to that one. So I'm going to draw an axis that goes down. I didn't do this very well, but I'm going to draw an axis that goes down through and goes that way. And that's going to be at a right angle to the parallel axis. Unfortunately, the word that is, I spelled that wrong, but you get the idea. That's a parallel axis, and this one's going to be perpendicular to the parallel axis. And the problem is P is already taken, so I'm going to call this one the P-axis, and I'm actually going to call this one the N-axis. And I've mentioned this. I think I mentioned this word before. This is called normal, and normal in physics and in math just means perpendicular. So rather than calling it parallel and perpendicular, we're going to call it parallel and normal. So I'm going to call the axis that's parallel to the axis the p-axis. I'm going to call the one that's perpendicular or normal to it the n-axis. So now I have a block that's placed on this incline. And now I want to look at the forces, because remember, this is a free body diagram. I'm going to look at the forces of this block on the incline. Well, if we draw the force, I'll do these in red so you can see a little bit better. I'm going to go to the center of the block, and I'm going to draw the force we always draw, and that's the weight. The weight is straight down. The weight is trying to go to the center of the earth. So it's always straight down towards the center of the earth. Now, when the block was on a horizontal surface, we had the weight pushing down, and we had the normal force pushing up. And we talked about that before when we did the friction lab. We had the weight pushing down, the normal force pushing up. That was Newton's third law of pair. They canceled each other. They were equal to each other. Yay, everything was happy. But now you can see this is not the case anymore. So what's happening is the weight vector is pointing down. My FW is going downward. And my normal force is going to be how hard does the surface push back up? Well, the surface now is right here, and the surface is going to push back up in this direction. So my point is, you don't have to draw this yet, but my point is this is getting a little bit more complicated. We have to be careful to understand what we mean by these words. So I'm going to clean this up a little bit. I'm going to get rid of the FW in that location. Clean this up a little bit. I'm going to relabel this FW, but I'm going to do it even finer. So I'm going to label this FW down below. So that's the weight vector, just like the weight vector over here is pointing towards the center of the earth. Now I want to break that, just like if I had a vector going at some angle, I could break that into an x component and a y component along the axes. I'm going to do the same thing. I'm going to take this FW and break it into components that are along the axes. And I'm going to pick a different colored pen now. I'll grab blue, for example. And what I want to do is I want to see how much of this FW is pointing down the incline. I'm going to draw this vector. And so what I'm doing is I'm saying how much of this FW, if I go to the tip of the FW down to here, this blue line represents the part of the FW that's going parallel. Now I need a name for how much of that weight is going parallel. So I'm going to call this FW for weight. I'm going to call it P for parallel. So, and we'll talk more about what exactly this is later, and I'll derive the equations for it. But all I'm trying to do is I'm trying to, like this situation over here, I'm saying, hey, I got a vector going at some angle. I want to break this into an x component and a y component. Could be a velocity vector, whatever. And in this case over here on the left, it made sense to call this, if this was FA, it made sense to call this FAX or FAY. And we did this, again, if this were a velocity, we'd call it Vx and Vy. All we're doing here is we're taking FW and we're breaking it into the components of the axes that exist. And our axes happen to be the parallel axis and the normal axis. So likewise, I can do the same thing on the other axis. I can say, well, how much of this FW is pointing towards the incline? And so again, I'm simply breaking that FW into an FWP and an FWN. Okay? So I've taken a vector that exists and I've broken it into two components along the axes. And now instead of using FW in my calculations for forces, I'm going to look at FWP and FWN. So if you want to stop the video and draw the picture of the block on the incline and label those two blue vectors as FWP and FWN, and I'll derive what the math is to show you that. So stop the video if you want and take a look at that, and we'll get squared away. Now I'm going to keep rolling here. So one of the things you'll notice is that when I slide myself over here again, one of the things you'll notice is that one of the ways of looking at what these things mean is looking at extreme cases. So what I'm going to do is I'm going to look at so here's what we just talked about. I got this block sitting here on an incline, and I have my N, my P, I have my P and my N axis. But I want to look at special cases. This is some arbitrary angle, theta. It could be 20, 30, 40, 50. Let's think about what happens if I make the angle 0. So if I don't have the thing inclined at all, and let's think about what's actually happening. So let me scroll down here a little bit. I'm going to take this angle of 0 and just think about our horizontal case. How much of this weight, remember the weight's pointing this way, how much of that weight is pointing in the parallel direction? In other words, how much of this FW, this blue vector, is going parallel, going left or right? Well, it turns out none of it. None of this vector is pointing left or right. It's all pointing down, straight down. And therefore, how much of it is pointing in the normal or the perpendicular direction? Perpendicular, you mean here it's parallel to this or perpendicular to this? Well, obviously all of it is. All of that weight is pointing down or in that normal direction. And same thing over here. We can come over here and say, well, now I've inclined this thing 90 degrees. So how much of this weight vector, remember weight always points to the center of the earth, and now my angle is 90. How much of this weight vector is pointing in the parallel direction? Well, my incline now is this way, and so all of it's pointing in the parallel direction, and none of it is pointing in the normal direction. So what I'm trying to show you here is that as I change the angle, the proportion of the P and the N portions change. And I'll show you that in just a different way. But I'm trying to get you to think of this conceptually rather than memorizing equations. I want you to understand where they come from. So again, that's not hyper important, but it's kind of useful. Now I'm going to show you a simulation here. Again, let me drag my face out of here. I said, therefore, as the angle increases, as I make this angle bigger and bigger, more of this, think what happens to the FWP. Think about what happens to the force that's pulling the block down the incline. And think about the forces pushing into the incline. Again, they're called FWP and FWN. Now, to show this to you, I have a simulation online that does it for me. So I'm going to go to the simulation. It's on OPhysics. And this is a little difficult to see at first. There's a lot going on my screen, unfortunately, because I have my face and I got this toolbar and some other stuff. But here's a block resting on a horizontal surface. The angle has been set to 0 degrees. So I have a block sitting on horizontal, and it shows exactly what I just showed. Weight is pulling down, and the normal force is pushing up. And that's that third law thing we talked about. That's one of the few things I wanted you to know about the third law, is that weight pushes down, and the table pushes back up, and that force back up is called the normal force. So when the angle is 0, it's just what we talked about before. But I'm now going to change this angle by inclining this incline, and you'll see that this weight vector will be broken into a P component and an N component. So they call it perpendicular for N, and the P you'll see in just a second. So let me crank up the angle a little bit, and you'll see this actually start to change. So now when I put this at some angle, let's say 18 degrees, now what's happened is that this weight vector still points to the center of the earth. But it's more convenient to break the weight vector into a parallel component, and they use the symbol for parallel, and a normal component, and they use the symbol for perpendicular or normal. They still label the N. So this weight vector now still points to the center of the earth. There's some angle here. It turns out this angle and this angle are the same. It's a math rule. And so I got my parallel component going down the incline and my normal component going towards the center of the earth, or towards the incline itself. Now, as I make the angle bigger, look what happens to the FWP. As I make this angle larger and larger, you'll notice the FWP gets bigger and bigger and bigger and bigger until finally, when I make it vertical, the FWP is the weight. So again, this is trying to show you that as the angle changes, these vectors change. So in other words, these vectors depend upon the angle. The vectors will get larger and smaller. You notice as the FWP gets larger, the parallel force gets bigger, the normal force gets less. And this is what goes back to the question I asked about a skier. If I have a skier on a slope like this, well, what's pulling the skier down the incline? This MGP, this FWP. But it's not very long. When I make the angle really steep, the skier gets pulled by a bigger force, and therefore they go much faster. If you ski down a slope that's 75 degrees, you're going to go like a bat out of hell. If I make the angle really low, you're going to go relatively slowly. So skiers have green slopes and blue slopes and black diamond slopes to give different skiers different abilities, a different experience. But it's all based upon this geometry. And if that kind of makes sense, that's great. Now, the rest of this you can memorize. I'd like to show you where it comes from, but so the base idea is the angle increases, FWP increases. And if the angle increases, the FWN decreases. Okay? Okay, I hope the video is still going. We'll see. I had to stop that because the bell rang for the last period. So anyway, we were seeing a minute ago that as the angle increases, the FWP, the part pulling it down the incline, increases, and as the angle increases, the normal force actually decreases because, again, both these depend upon the angle. Um, Now, what I want to do is I'm going to give you an equation. You're going to memorize it, or you're going to understand where it came from. But first of all, let's define these things, and let's write the equation for them. So if I want to find the component of the weight that's going parallel, we know the weight always equals mg, and the component is going to kind of give a percentage. It's not really a percentage, but it's kind of like how much of this is going this direction, how much is going this direction. So what we do is we multiply to get the p component, we use the sine of the angle. Now, I'm not showing you the derivation of that. I'm not going to do the math on that. That's something you just need to memorize. I had a student one year actually say, oh, that's easy to memorize. And he said, because P goes with S because it's Peter Schmidt. I was flattered. I teared up a little bit. But if that helps you memorize it, that's great. Avoid the temptation of thinking of the P as the X and the N as the Y. You don't want to do that because, first of all, it's not. And that will confuse you because the X always goes with cosine and the Y component always goes with sine. This has to do with the geometry, and I'm not going to derive it out, but just trust me. The P component, the part pulling down the incline, is always associated with the sine of the angle. Now, so this is how you calculate. This is the equation, and you should memorize that. So FW always equals mg, and the P component goes with the sine. So it's not really difficult memorization. So this is a part of the component of the weight that tries to pull an object down the incline. So the reason I'm saying this is that I have kids sometimes draw FWP going up the incline, and that's impossible. Weight always pulls things down. So if you draw FWP going up, I know you have no idea what it means. It's part of the weight trying to pull it down the incline. Now, by the same logic, we can come over here and say, well, FW equals mg. And if you had to guess, you'd probably guess, well, the n component is going to be not the sine, but the cosine. And so the kid that proposed the PS for P. Schmidt, I said, well, what do you got for the other one? He goes, oh, it's easy. It's Nicolas Cage, the actor. Now, this was 20 years ago when Nicolas Cage was actually in movies, but if you know who he is and that helps you, that's great. So just remember P. Schmidt and Nicolas Cage. That this will allow you to calculate the components, and we need to be able to do this often. Now, what is FWN? Well, that's the force trying to pull the block onto or toward the incline. And I'll come back and show you this in a second. So again, there is some memorization, and it'd be great if you could see where it came from, and I can show you that sometime later, but you need to know what these things are and how to calculate them. We use them a lot in the Yukon class. So the good news is, oh boy, so here's a happy little girl, a happy little boy. Look at this dog. He's airborne like Superman. His legs are straight out and straight back. What this now allows you to do is solve a whole bunch of really cool problems. Okay, and when I say really cool, I mean semi-cool. So I'm probably going to stop here and I'll come back and do a couple examples in a second. I think my video actually shut off anyway, so we'll see what happens.